On 17th March 2025, BYD introduced a 1000 kilowatt DC fast charging for their upcoming EVs. That's 1 megawatt of fast charging, and it's incredible and phenomenal. What it means is 400 kilometers of charge in less than 5 minutes. So that brings EVs right into the territory of ICE engines in terms of refueling. We are not going to discuss about that news in particular in this episode, but you would have seen that BYD has come up with a 1000-volt architecture for their batteries. And you would have heard of 400-volt architecture, 800-volt architecture for the EVs. Today's episode is exactly going to be discussing on these architectures of EV batteries. Hello everyone, welcome to the Green and Clean YouTube channel. My name is Vittal. If you are new to this channel, do check the video sections of this channel. There's going to be a lot of good videos that you might want to watch. So let's get started with today's episode without further delay. At the basic premise of today's episode is based on this formula for power. You would have read this in your school days, but nevertheless, power is equal to V into I, or voltage into current. So that's the formula we all learned. And you also know that voltage is equal to resistance into current, or V is equal to R into I. So that means power is equal to R into I square. These are two equations, but we are mostly going to look at P is equal to V into I in today's episode. Now let's look at the smallest unit of a battery. It's a single cell that you can see in this picture. And if you want to know how a single cell works, I have covered the video previously. You can find it here in the I section of the video. So this particular cell has a nominal voltage of 3.7 volts. Usually the voltage may differ, but let's for this discussion, let's take the nominal voltage as 3.7 volts for this battery. Now what does this mean in terms of what this battery can drive? Let's say theoretically we want to drive a 75 kilowatt motor using this battery. So how much current does it mean for this battery? So I is equal to P divided by V as per the previous equation. So that's 75,000 divided by 3.7, which comes to roughly around 2000 amperes. And that's a whole lot of current. So it's practically not possible that this small battery can drive so much of power. So what is the actual current that this battery can take? It's 2.5 amperes. That's way less than what we need to drive this whole motor that I showed in the previous picture. So that means we need much more than one cell to power a 75 kilowatt motor, right? So that means we need to connect these batteries together either in series or parallel and get the desired power out of this whole battery pack. So how do we do it? How many batteries, how many cells do we need in series? How many cells do we need in parallel? What exactly is a battery architecture? So that's what we are going to discuss here in the next section. So before we go further, let's go back to this single cell. So 3.7 volts is the voltage. If 2.5 ampere of current flows through this battery for 1 hour, then this cell will be empty. So the capacity of this single cell is equal to 3.7 volts into 2.5 amperes and the 1 hour that it takes for this cell to discharge. So that roughly comes to around 9.25 watt hour. So this is important. Single cell of 3.7, the power, the capacity is 9.25 watt hour. Now let's try to connect two such cells in series. When you connect these cells in series, the voltage gets added. So its current voltage is 7.4 volts, that is 3.7 plus 3.7, and the total capacity is just added. So you have 9.25 0.25 watt hour, so multiplied by 2, so it's 18.5 watt hour is the capacity of this cells which are connected in series. So what is the maximum current that it has to pass through to power a 75 kilowatt motor is 75,000 divided by 7.4 volts is equal to 1000 amps. So that's still a lot of current, and it's still not possible for these two batteries to just power this motor. Now let's try to connect these batteries in parallel. So when you connect the batteries in parallel, as you see in this picture, the total voltage remains the same of the single, which is equal to the single battery cells voltage, which is 3.7 volts in this case. So in this configuration, it has 3.7 volts of voltage, and the capacity is again the same, 18.5 watt hour, and the maximum current is 75,000 divided by 3.7 volts, which comes to roughly around 2000 amperes. So a lot more current with even with this combination. By the way, when you pass just 2.5 amp through this battery, these two batteries connected in parallel, it's going to run for 2 hours because you have connected it in parallel. In the earlier example, when you connected it in series, it has a higher voltage, but if you pass 2.5 amps, both the whole unit will be discharged in 1 hour. So connecting in parallel increases the duration with of the pack. Connecting it in series increases the voltage of the pack. But we are still very far away from powering these 75 kilowatt motor, right? So we need lot more voltage and lot more cells to drive this motor. So let's now discuss more voltage, a 400 volt architecture, right? So what exactly is a 400 volt architecture? Uh, if you have 3.7 volts cells like this and you connect it in series, and you want to achieve 400 volts in this pack, then you need to calculate how many cells you need to connect in series, right? So that you can calculate simply by dividing 400 volts by 3.7 volts, which comes to roughly around 108 cells. So if you connect 108 cells in series, then you will get 108 into 9.25 watt, or 1 kilowatt hour capacity of a battery pack. So in this picture, there are not 108 cells, but just imagine that there are 108 cells in this pack that you see here, and you have a 1 kilowatt hour battery pack. Very good. So let's see what this battery pack can do. Let's connect 75 kilowatt motor into this battery pack. So how much current does it draw now? So 75,000 divided by 400 volts. Now we have 108 cells, so 400 volts. It takes 187 amps. So pretty much manageable current, 187 amps. And how long does this battery last? If it takes the whole 187 amps all the time, so it lasts only 48 seconds. So if this motor takes the whole 75 kilowatt of power through this battery pack, it is going to last only 48 seconds. So we still are very far away from achieving some real life range or a real life usage of an EV battery. So let's proceed and see what we need to do next. Obviously, you cannot add more and more batteries, make like a 2000 battery cells in series. That's not going to work. So how do we fix this problem, right? So next comes what is called as connecting these modules in parallel. So in this example, you have the same cells in a module, 108 cells in a single module, like a vertical stack of batteries that you can see here. So that's like a single cell, that's like a single module, sorry, 108 cells in a single module, and you connect such modules, 10 such modules in parallel, and you get like a total number of cells of 1000. So you use 1080 cells, and you get a capacity of 10 kilowatt hour. So 1080 multiplied by 1080 cells multiplied by 9.25 watt hour is roughly around 10 kilowatt hour of battery. And if you connect this to 75 kilowatt motor, then you are going to get a lot more efficient battery that can power this motor. So that's in a gist how you can design. Let's take an example of designing a 50 kilowatt hour battery with a 400 volt architecture, right? So let's take it step by step. As you can see in the from left to right. So first we need to calculate the number of cells. So number of cells is simply total capacity that we want to design divided by the capacity of one cell. So that's 50,000 watt hour, or 50 kilowatt hour is 50,000 watt hour divided by 9.25 watt hour. So we need around 5,409 cells to make a 50 kilowatt hour battery pack. Now, how many cells in series, how many cells in parallel? We need to see what is the desired voltage. We said we will design a 400 volt architecture. Well, a 400 volt architecture doesn't exactly mean 400. It will be roughly around 400. It could be 350, 370, 400 or 450, something like that. So let's target 370 volts, because if you connect 100 cells in series, you get 370 volts. So let's do that. So 100 cells, so you have 370 volts architecture battery, which is roughly 400. And how many cells you should connect in parallel? So that's number of cells required divided by the number of cells in series. So that's 5409 divided by 100. So roughly around 55 such modules you need to connect in parallel. So the way to go about building this 50 kilowatt hour battery pack is connect 100 cells in series, create a module, then prepare 55 such modules of 100 cells each, and connect those 55 more modules in parallel, and then you get a 50 kilowatt hour battery pack. I hope this makes some sense so far. So if you like this video, please like the hit the like button, subscribe to the channel, and press the bell icon. It helps a lot to me and also hopefully to you. So let's continue with our episode. So with the same battery pack that we built with the 400 volt architecture, what is the power that is, what is the current that is flowing through this battery, right? Now you would have seen in many EVs some sort of an energy meter which tells you how much power the car is consuming from the battery. Usually it goes around 10 to 20 kilowatt, but when you accelerate hard, it can go up to 30, 40 or something like that. So I'm taking an example of a peak throttle which can take this energy meter consumption up to 40 kilowatt. So to draw 40 kilowatt of power through this 400 volt architecture, what is the current? So it is 40 kilowatt divided by 370 volts, which is 40,000 divided by 370 is equal to 108 amps. So 108 amps of peak current may flow through this battery. It's not all the time, but when you accelerate hard, when you go fast, 108 amps of current will be drawn from the battery. So what does it mean for fast charging with such an architecture, right? So we have a 400 volt architecture battery, and if we go at a 80 kilowatt fast charger, DC fast charger, then you are looking at 80 kilowatt divided by 370 volts, which is 80,000 divided by 370, which is equal to 216 amps. So 216 amps is the current that flows through this whole EV and the battery and the system. That's why you would have seen in some of the DC fast chargers, the cables are really thick, and sometimes I struggle to pull it out because they are heavy and they are thick. So that's the reason. A lot of current flows through these cables, and that's why it is thick. All right. That's 400 volts architecture so far. So what is 800 volt architecture. It's the same principle, it's just the number of cells in series and parallel that will differ. So for an 800-volt architecture, first you need to decide how many cells of 3.7 volts you have to connect in series. So that's 800 divided by 3.7, it comes to roughly about 216 cells. That's twice the number of cells in the 400-volt architecture. So you connect 216 cells, each cell has a capacity of 9.25 watt hour. So this makes it a single module of 2 kilowatt hour of capacity. And if you connect this to 75 kilowatt motor, then you are looking at 75,000 divided by 800. So 94 amps of current flows through the wires that you connect. So if you can see, compared to the 400-volt architecture, the current is exactly half or less than half of what is there in the 400 architecture. And how long does the battery last? Again, it's the same calculation, 2 kilowatt divided by 75 kilowatt, and it's roughly last around 96 seconds. But we still need to work how many more modules we need to add, because we have more cells in series inside the module. We need less modules to be connected in parallel. In this case, exactly 5 modules. So 216 cells in series inside a module, and you connect 5 of such modules in parallel, then you get a 10 kilowatt hour battery pack, and that is usable with this cell. Now let's look at the same battery that we designed earlier, 50 kilowatt hour battery capacity with 800-volt architecture. So first we need to calculate the number of cells. The number of cells is going to be the same whether it is 800 volts, 400 volts, or even 1000 volts architecture, right? So it is 50,000 watt hour divided by 9.25, which comes to the same number of cells, 5,409. What makes the difference is how many cells we connect in series. So for this example, let's take 777 volts, which is roughly very close to 800 volts. So 77 volts divided by 3.7. So you connect 210 cells in series, and then number of cells required divided by the number of cells in series, which is 5409 divided by 210. So you are talking about 26 modules. So to build the same battery, 50 kilowatt hour battery with 800-volt architecture, is you connect 210 cells in series and create a module, create 26 such modules of 210 cells each, and connect them in parallel, and then you have a 50 kilowatt hour battery pack. Now let's look at the current. So it's the same scenario. Let's say your EV is trying to pull 40 kilowatt from the battery. So 40 kilowatt divided by 800 watts, 800 volts, sorry. So 40,000 divided by 800, it's 50 amps of current. So it's again half the current of the previous case. So if you have a EV with the 800-volt architecture, for the same amount of power, it takes roughly half of current. So 800-volt architecture means you can design the EV for extracting less currents. Let's go on. What does it mean for fast charging? So again, 80 kilowatt charging, DC fast charging divided by 800 volts, it roughly comes to about 100 amps of electricity through the wires. So that means if you have a 800-volt architecture supported fast charger, it can work with thinner cables compared to 400-volt architecture scenario that you have seen earlier. So that's in a nutshell about 400 volts and 800-volt architecture. Now, what are the advantage after going through all this while all these minutes? You want to know what is the advantage of 800 or 1000 volts architecture with when you compare it against 400-volt architecture, right? So as you have seen, the first advantage is there is a less current flow through the battery and its component. So when you have less current flow, it leads to thinner and lighter cables all around in your EV platform. So this reduces the overall weight of the EV, and also because of the thinner cables and lighter cables, the motor uh, can be designed more efficiently. So you can have a same power motor which is of smaller size in the case of a 800-volt architecture. Less current also means less loss of energy. So you have less loss of energy due to heat. So less current flows, so less heat. So you have more efficiency in the overall system. And the next point here is the faster DC charging, which is how this all started, right? So if you have the same thick cable that you see in the fast charging, and it can dispense, let's say, 200 or 300 amps of power, or even of current, or even more, then because you have a higher voltage battery, you can fill in more capacity to the battery than a 400-volt architecture. So this is what exactly as what made the BYD come up with 1000-volt architecture, which can charge up to 1000 kilowatts in a charging session. So that's how they have achieved it. And last but not the least, because of all of these improvements, less current, less weight of the EV, efficient motor, less loss of energy, you are talking about nearly 15 to 20% of range being improved or increased when you have a 800-volt architecture compared to 400-volt architecture. Now, the caveat is because a 800-volt architecture needs more cells in series, you are connecting the cells which are, let's say, of this size and 200 of them. So you have a battery pack where one side of the battery is longer in the case of an 800-volt uh, architecture when compared to 400-volt architecture. So that's why these batteries with 800-volt architecture are difficult to fit in smaller cars, because you have one side which is pretty long and the car has to have that much length. So that's why 800-volt architecture is mostly used in slightly longer cars, and not in like a compact or a hatchback kind of cars. Maybe in the future there will be some ways to fit these batteries in even in the smaller cars. So that's what I wanted to discuss today about the 400-volt and 800-volt architecture. It's really simple. It's just a formula, a maths, and then just arranging the cells. But of course, once you have a battery pack, you need to design the whole system around it so that it can be safe to operate. So remember, a higher voltage EV has to have safety, because higher the voltage, you are compromising on the safety. So you can't really just go from 1000 volt architecture to 2000 or 3000-volt architecture just like that. You have to have a better design to take so much of voltage and have a very safe car. So that's why it takes time to design these systems. So that's the explanation. None of this explanation is like highly scientific. I'm not an electrical engineer, but I'm just try to explain it the way a common man can understand. I hope you like this video. Thank you very much for watching. See you again in other episodes of Green and Clean YouTube channel.